But it comes down to symmetry, and I'll try to kind of show you what I mean by symmetry. But remember a while back we kind of did trends, like if this is different, then your boiling points will be different. The different ways of getting high or low boiling point temperatures. So now you can add with regard to melting point temperatures, in addition to all the other stuff, it's symmetry. So increased symmetry, okay, basically think of that as increasing your intermolecular forces for solids. And that will increase your MP, melting point temperatures, MPT. Sometimes, I guess instead of MPT, it's just temperature MP, melting point temperatures. So symmetry, and you're going to kind of, I don't know if I convince you or not, but that's what it is. And again, it just has to do with something transitioning from its solid to its liquid phase, melting. So we have these two compounds. They're both types of F something because we have two carbons. Carbon is a double bond, not a single bond. So instead of an ethane, it's an ethene. E-N-E is the double bond. And we have these two options. The one thing about double bonds is did I read you this slide? Okay, good. Because I feel like I remember talking about rotation. Anytime I have a double bond like you have between those two carbons, it can't free rotate, it's stuck, it's rigid. So we have these, and this is a planar molecule. So we have these options literally of the two chlorines being on one side, and if I'm like a cheerleader that's like this, we call that cis, but if they're on opposite sides, like you see over there, we call that trans. Okay, so cis, trans. I think I did talk about that maybe when we talked about nomenclature. Okay, so trans means they're on different sides. So it's an ethene. In this case, yeah, and I guess in both cases, it's 1,2-dichloroethene. In this case, it's cis. In this case, it's trans. Okay, so that's it. All right, with regard to polarity, do we buy this? That here, the centers, the chlorines are going to be partially negative. They're pretty high electronegative. So you figure though the center of that high electronegativity is going to be right here. Does that make sense? Spatially, it lies in a plane. Okay, and the center of the carbons here, the center of the hydrogens, everything kind of converges in the center. So when centers of positives and negatives coincide, that makes that a nonpolar. This one over here, where would the center of the chlorine atoms be? Be right here, yeah. So definitely that's what makes this polar, okay? And one of the things we know about polar is with regard to the boiling point temperature, which one would have the higher boiling point temperature? How many people think it's the polar one? I do too. Because they're non-polar, you just have to have the only way you can something non-polar stick together is those weaker induced dipole. Yep. So higher boiling point temperature, polar. That's awesome. Now this is an example though where I'm going to try to show you why this has more symmetry. So when it comes time to transition from its solid state to its liquid state, actually you have to bump it with more energy. Okay. So I always get confused. I don't deal with negative temperatures very well. So you're like negative 50 versus negative 80. Okay, this is actually, I know it seems cold, but this is a warmer temperature than this. This is a warmer temperature. I have to pump it with more energy. Well, it's nonpolar. What's going on there? And it goes back to what I said. It's more symmetrical. So to kind of show you the way I think of it, where is the symmetry there? Well, it's kind of we'll put it this way. To me, I see symmetry here. I see symmetry in like a plane. It looks like a mirror, right? Over on the other one, I see symmetry as a point. It's more symmetrical. Around this point, we have these two, we have these two, and we have these two. They kind of paired up around a symmetric point. So anyway, for what it's worth, that's how that works. The transversion is more symmetrical, and thus it has the higher melting point temperature. Even it has the lower boiling point temperature. This is something that we talked about. We talked about intermolecular bonds. That has to do with solids instead of liquids. But along the x-axis, you see increasing number of carbons. And then along the y-axis, you see the temperature at which the substance will melt. So like we talked about before, as you increase numbers of carbons, then you increase the ability for that induced dipole, And they're just, the last one I need to mention is, of all of these things that we talked about the other day, we did not talk about the amorphous solids. I will have a couple of slides to talk about that. Remember, amorphous solids are just disorganized. It's funny, and especially in some sort of chemistries like organic chemistry, the way you take the way things crystallize, the rate at which they crystallize, the temperature at which they solidify, is a player with regard to whether you're going to get something amorphous or something that's crystalline. So, yep. The thing about amorphous solids then, when they break, it's not going to cleave into nice shapes, okay? It's going to be kind of random. I don't think you can get 7 years bad luck just by looking at one of these. Okay, so I think we're okay here. But with this broken mirror, actually glass is an amorphous solid. And I mentioned temperature as a player with regard to whether you're going to get amorphous solid or crystalline solid. And on purpose, that's the way silicon dioxide is treated to create glass. Because it can also be a crystalline solid. This talks about treating it with heat, and you can take something that's crystalline and make it into something that is amorphous. All right, so these will be due Friday. Let's see what else we got now. I'm trying to pay more respect to that clock in here because it's off, so I'm gonna try not to hold you guys over. I said I'd try. So far, among other things, I feel like we've talked about kind of the vapor, like vapors. We've talked about liquid, vapor, and then just now we kind of talked about solids and liquids. Okay, we can actually throw the liquids and the vapors and the solids up on a table, and it's called a pressure temperature phase diagram. Now we're all kind of really familiar with the whole temperature thing. By golly, you know, we talked about how you can take a solid, pump it with energy and it will melt, and you can take a liquid and pump it with energy and it will gasify. And actually, when we do that, we're thinking, well, the pressure, duh, it's like 1 atmosphere, right? So we could actually here kind of think of that in terms of being up here. If this is 1 atmosphere, okay, I'm going to increase the temperature from left to right. It's going to start as a solid, going to add more energy. It's going to melt, liquefy. I'm going to add more energy, and I know it's not over here, but then it's going to turn into a gas. That's it. That's all a phase diagram is. But we have this pressure component, which everyday chemistry we don't think about. When you, and I don't have any in here, I used some the other day, but like if you want to clean off your keyboard, you get like compressed air. Compressed air, if you shake it, you'll hear the liquid. So basically what compressed air is if we could go at it, it would be something under high pressure under normal temperatures. Okay? Compressed air. You can take a gas and make it into a liquid if you put enough pressure. You can take a liquid and make it into a solid if you put enough pressure. Let's look at it this way. Let's say that this is our air over here. Let's say that this is room temperature. Room temperature. okay? Room temperature, right? And we'll call this, now this is going to be my 1 atmosphere. I know I'm kind of messing this up. So room temperature 1 atmosphere. I told you you can take a gas, increase the pressure, and it will liquefy. You can take a liquid, increase the pressure, and it will solidify. That's kind of what I'm showing here. That's what we call an isotherm. We're just jacking up the pressure. Liquefy, solidify. It's a pressure, temperature, phase diagram. So pressure, temperature, phase diagrams kind of look like a Y, like this. Solid, liquid, gas. Those are the sectors where the substance is going to be that particular phase. As you might imagine, pressure, temperature, phase diagrams vary with the compound. Okay, so we have to say which compound it is. Pressure, temperature, phase diagrams. So, let me go back. Oops, sorry. I'll erase all this stuff. And they make sense. Things should make sense. So, for instance, at low temperatures and high pressures, we expect things to be solids. At intermediate temperatures and intermediate pressures, we expect things in general to be liquids. Now, again, it has to do with intermolecular bonding, right? But at high temperatures and low pressures, we expect things to be gases. So those 3 sectors. Here is actually one for, it doesn't say what it is. But you can see the Y there. Okay. Now, the thing is, for this Y, can you see where, if you go back and forth, like over here, you're liquid. Over here, you're solid. Liquid, solid, if you're along that line, okay? Of course, we would call that melting and that freezing. Here, along this transition, you know, if you're over here, you're a gas. If you're over here, you're a liquid, okay? Of course, we call that vaporization or evaporation. We call this condensation. And last but not least is this one right here. This is the funnest, right? Because if you look at the sectors that it separates solids and gases. So this is the fun one where it skips the liquid state, right? Sublimation or deposition. So we know, for instance, solid CO2 will sublime, go into its gas state. By the way, solid CO2, you know how they got it solid CO2s, CO2 is a gas. They cooled it down and they pressurized it to make it from what would be a gas under normal atmospheric temperatures and pressures to solid. So anyway, sublimation, and if something goes from a gas directly to a solid, we call it deposition. So those transition states are associated with going across those lines. The other thing about pressure, temperature, phase diagram is this important part, place right here, triple point. Is that not fun or what? You're like, so visually looking at it, you're like, triple point, well, what phase is it? Well, it coexists in all 3 phases. That's so awesome. Triple point. We'll talk more about this point up here is important. It's called the critical point. And you might think it's like well, it's a Y. It just kind of looks like, you know, in math, sometimes we have these things, these lines that just go on forever. It does not go on forever. This one doesn't go on forever. It has an abrupt stop, the one between the gas and the liquid. And that abrupt stop is called the critical point. This other one, it goes on forever. I'm cool with that. Okay, the one between the solid and the liquid, but you're going to see an abrupt stop.
What's beyond the critical point then?
We'll talk about that.
Oh, sorry.
Yeah. And actually, it creates a 4th sector. Yep. So this is for water. Now, slopes, I don't know if you're okay with this, but straight lines can either slope positively or a straight line can slope negatively. And actually, especially this is to me the only straight line. You would expect the line that separates the solids and the liquid phase to be a straight line. You see where this is a negative slope. Most materials have actually a positive slope. This is the negative slope associated with the pressure temperature phase diagram for the substance we know and love called water. Okay? So
is there a point when the pressure is so high that, like, no matter what temperature you won't be able to get the water?
the pressure's so high that it's just going to stay ice, you can get it to liquefy.
Or like even like you couldn't turn the liquid into a solid because the pressure is so high, like at a regular temperature. With the pressure way high, like obviously the negative slope's going up, so it's going to keep going backwards, right?
Right, it's going to keep going backwards. So you're saying if you go back to like absolute zero or something?
Or even just like that 100 degrees Celsius. Like, so the temperature has to be low for it to solidify.
The sublimation part has to be below point B, below the triple point.
I'm just curious, like, the pressure, like you see as the pressure increases, the chances of it becoming a solid are less and less.
Right.
So,
Or to me, the chances of it becoming a liquid are less than, no, oh, yeah, solid is less and less, yeah. Because this will decrease, get smaller and smaller.
so if the pressure's high, then would the freezing point of water be lower? Not
Actually, that's one of the things I wanted to point out. Because like, let's see, what temperatures do we have down here? This is degrees Celsius. So 0 degrees Celsius is the temperature at which it normally freezes. And our freezing point temperature is, we pick up right, this is, I wish it was in atmospheres, but it's kilopascals. So this must be atmospheric pressures.
That makes sense. So we know it freezes. We know water freezes at 0. So right here, where it intersects this line, that actually is what normal atmospheric pressure is. Okay, so this is normal atmospheric pressure. But it's kind of like these, whereas if we take and increase the pressure, our solid water, what's going to happen to our solid water? It's going to liquid. Yeah, our solid water will liquefy because of this negative slope if we increase pressure. And then the coolest thing, I don't know if you're into like ice skating. I'm not an ice skater, but it's beautiful to watch. But you figure any skater, they have the whole mass of their body on like blades that are, I don't know how big they are, but a pair of blades like this. Their whole mass is like, okay, so basically we have a lot of pressure under there. So as it turns out, the reality is they are in the vicinity of their ice blade, creating the conditions where their solid ice is actually liquefying. So that's part of the dynamics for ice skaters to do what they do. So, but I think you're definitely right. So the negative slope is what allows that all to happen. A positive slope is kind of a different creature. Most things have positive slopes. Yeah. I don't know if I answered your question, but that's pretty cool. Okay, so again, negative slope, again, this is water. So sometimes, and I don't give you too many hints about the test and all that, but sometimes on the test for this unit, I'll put like a pressure temperature phase diagram, and I'll ask you generic questions. So for instance, hopefully you recognize right away I would put solid, liquid, gas. Okay, we'll be talking more about that. But can you see where the BC curve, okay, is separating the vapor, the gas from the water. So that would be what the boiling point. So it would be like condensation and evaporation. Okay, does that make sense? Now the next one, it says you find AB curve. And this is my favorite. So AB curve. This is where, I wish this throws me off because it's water. I shall think of liquid water, but this is the gas and the solid. So that's the sublimation or deposition. And the BD curve looks like it's separating solid and liquid, so that must be the melting and freezing. Cool. B is the triple point, point B. And point C is the critical point. And like I kind of said, you make I think it's like another physical phase of matter. You know, we have physical phases, solid, liquid, gas. It's another physical phase, I think. So I mentioned this before. We can pick off, how does this work? Yeah, this would work. Think of this way. Along the pressure, if you, in the dot right here, if you dot in what atmospheric pressure is, which I don't deal in kilopascals very well. To me, it'd be 760 millimeters mercury or 1 atmosphere, but 101 kilopascals atmospheric pressure. So if you see where it intersects your two lines, then bada boom, you have picked up the freezing point temperature of the substance from its pressure phase diagram, and bada boom, you have picked off the boiling point temperature, okay, where the normal pressure intersects with this segment right here. And this segment right here, you come down and measure the temperature. Because water boils at 100 degrees Celsius. So the freezing point or melting point, same thing, boiling point or condensation point. Now this one, it's not water, because I can tell because it doesn't have that kind of characteristic negative slope. This one is the pressure temperature phase diagram for iodine. So iodine under normal pressures and temperatures is a solid, so hopefully we can see that. Let's see. With regard to Celsius temperature, we're looking at about 25, okay? And 1 atmosphere, finally we're back into atmospheres instead of kilopascals. But can you see where it falls? Those ordered pairs of normal temperatures and pressures falls into the solid sector. So this one, I guess I have a beef again with OpenStax. I don't like this. It's not the way I learned it. Not to mention they use kilopascals, which drives me nuts, and they kind of show this, which this might be true, it maybe doesn't go straight up, but this SCF stands for supercritical fluid. The supercritical fluid, so I just don't like this. Let me, on this diagram, in case I don't come back to it, let me talk about supercritical fluid and that 4th phase of matter. I'm making up things, okay? But you should be able to kind of think about, this is my temperature, this is my pressure. I'm going to draw kind of a Y in there. I'm going to draw a minus straight line, triple point. This one keeps going, and this one has an abrupt halt. This will be my solid, liquid, gas. So that's kind of what we have going here. So this abrupt point, called the critical point, to me kind of creates this way and this way another sector, okay? And that other sector actually is going to be supercritical fluid. Supercritical fluid. SCF. Bottom line is, can you see where supercritical fluid is warmer than, so T is greater than the critical temperature. And can you see where the pressure is greater than the critical pressure? Where if I go ahead and I say what the coordinates are there, they are, see it's x, y, so it'd be T sub C, P sub C. Supercritical, that's a supercalifragilistic.
Is that another thing that's wrong with the next graph that you started to show us?
Yeah, I don't
that this
like
whole panel is?
Yeah. And I asked my husband about last night, and it was kind of late, granted, and he's like, I don't know. So yeah, he said, yeah, I don't think of it like that either. but kind of think of it as another sector. And so now right away you can see to get a supercritical fluid, you need to have relatively high temperatures and relatively high pressures. Supercritical fluids, I'll go ahead and tell you, they behave like gases and liquids. They're a cross. They are so cool. I just think that's, actually they're hot. Okay, so triple points. And actually the triple point of water is just a little bit what we see warmer than 0 degrees Celsius and lower pressure than atmospheric pressure. The triple point, where basically things, all phases, not supercritical fluid phase, but are in equilibrium. The critical point is the abrupt stop, the abrupt end of this that separates the liquid and the gas. Yeah, this one. When we were talking about equilibrium vapor pressures for different substances, and actually this is what we call the equilibrium vapor pressure curve. So this right here is the EV for equilibrium vapor pressure curve. Why? Because it's the separation between liquids and gas. All right. So I'm going to show you a video, and it's going to show you how we can take is it a liquid? I think so. Take a liquid in a closed container, and we jack up the temperature, and then actually just jacking up the temperature is also going to jack up the pressure. So jacking up the temperature will have two things. It'll jack up the temperature and will increase the pressure, and you can get your liquid to go into supercritical fluid. Okay, so in supercritical fluids, the density of the liquid will decrease until the liquid basically becomes a vapor. But you figure if it's approaching this region, then your vapor is really squished together, so it's behaving kind of like a liquid. Because if we increase pressures, that's a tendency to make a gas go into a liquid. So the little video kind of, you'll see the liquid in the bottom and kind of gas in the top, and eventually they will kind of become one, supercritical fluid. It sounds like magic, but it's not. So the critical point kind of creates, I think, a fourth sector. So critical pressure then is the pressure at which your abrupt halt on your equilibrium vapor pressure curve ends, and then critical temperature is the temperature at which it ends. So warmer than this temperature, you cannot get it to become a liquid, no matter how you try, because if you increase the pressure, it's not going to go to liquid, it's going to go to supercritical fluid. Okay, supercritical fluids. I must be coming out here in a minute. So I kind of already said that supercritical fluids kind of behave a little bit, they're like a hybrid. They have the permeability of a gas because they're low density, but they have the kind of the extraction power of a liquid because they're high pressure. So actually for people like me who, I drink decaffeinated coffee, so I know there's a little caffeine in it, but if you drink decaffeinated coffee, they probably use supercritical fluid to extract the caffeine from those cute little coffee beans. Okay. So here's a still image of of the short little video I'm going to show you. Let's see what it is. So this actually, you see the liquid here and the gas here. This is at a temperature below the critical temperature. And this is jacking up the temperature. And as you jack up the temperature, actually the pressure is also going to increase. And this was what I was telling you. You know, you can see liquid, but you really can't see that. You barely see something here, but it's now a supercritical fluid. This, I was like, I don't know, I read the caption, this is from OpenStax, and I was like, really? I did not quite understand it. So anyway, that's when I went out and got this, instead of carbon dioxide, it's helium, but I thought this video did a good job. That's right. Carbon dioxide usually makes a pretty good supercritical fluid because you figure room temperature is, 298 Kelvin? So at 304 Kelvin, then you're actually into supercritical fluid region. Pressure is up there. Okay, but water is kind of a harder one to jack up the temperature and the pressure. So this was the, I think this is supposed to be the caffeine molecule that we're trying to get extract from our little coffee beans without hurting the coffee bean. I liked the video we saw because it kind of said that it's more, to say its viscosity goes to 0, supercritical fluid, so there's no resistance for it to penetrate those what it's trying to extract. So you put your beans in here. Let's see. Yeah, supercritical fluid is supplied from the bottom, and then the waste, the carbon dioxide and the caffeine is extracted through here. It can be you get the caffeine out, and then you put the refreshed supercritical fluid back. And then your decaffeinated coffee beans come from the bottom. So, ta-da! That's it for today. So we have those 2 parts that are due on Friday. And lab tomorrow is the Clausius-Clapeyron plot. Which is it? Which experiment is it? 5? 5? Okay, thank you. Experiment 5. Yep.
On the last exam.